See the expression for rate constant of zeroth order can be given as K0 is equal to A naught minus A by T. Okay. See in this, A naught is the initial concentration. A is the concentration left after time t. Okay. Now, if you want the amount that has reacted, it can be taken as A naught minus A. Okay. Reacted in time t. Okay. Now, the same thing can be expressed in a different format. Let me give you. Say this A naught minus A by T can be given as X by T, a different format. See, in this particular format, A is used to represent initial concentration. X gives us information about the amount reacted. Then A minus X is left out. Okay. So even this way also it can be expressed. K naught, sorry, K0 is equal to X by T. Okay. So this way we can give the K0 or the rate constant for zeroth order expression in two ways. Now let us see the expression for half-life. Every time we'll be going for two expressions. One is for rate constant, the other one is for half-life. First of all, what is half-life? You know, it is the time taken for the initial amount to become half. For the initial amount of the reactant to become half or to react half. Okay. So here, let us consider T as T half. See, when half time is over, amount left out can be given as taken by 2, because half time is up, half time is over. Amount left will be, of course, half of what we have started with, or half of the initial amount. Okay. Of course, the same can be given in some other terms as, you know, reacted is equal to taken by 2 in these terms. X is equal to initial by 2. Now let us substitute the things in K0 expression. So K0 is equal to A naught minus, see, A is nothing but A naught by 2 by T half, right? Now this can simply be given as T half can be given as A naught by 2 into, of course, this K0. So this is the expression for T half for zeroth order reactions. Now coming to this, it can be given as K0 is equal to straight away A by 2, because X is A by 2 and now T is T half. Therefore, T half can be given as A by 2 into K0, right? So this way, we can give expressions in two different ways, okay? So remember, every time we'll be going for two expressions. One is for the rate constant, the other one is for half-life. Now let me give you examples for the zeroth order reaction. Yes. The one that we have already discussed, H2 plus Cl2 in the presence of sunlight gives rise to 2HCl. Okay. Then we have decomposition of ammonia on the surface of platinum. Look at the stoichiometric coefficient, 2. But when you go for the rate expression, it will be rate is equal to K into ammonia to the power 0. It's a zeroth order reaction, right? Then even the decomposition of phosphine on the surface of nickel to form phosphorus and hydrogen. Then the decomposition of hydrogen iodide on the surface of gold. All these are zeroth order reactions. Okay. Now, of course, the first order reaction will be similar to what we have seen till now with some basic differences. First of all, what is a first order reaction? See, if the rate of a reaction depends on just one concentration term, it is called first order reaction, right? Earlier it was in case of zeroth order, it was on no concentration terms. Here it is on one concentration term. We can also say in some other way as if the rate of a reaction depends on or is determined by, let me write it this way. is determined by the change of one concentration term. It is known as first order reaction. Okay. That means rate of reaction depends on the first power of a concentration term. Now, this one concentration term can be given as the first power of concentration term of a concentration term. Let us take it in mathematical way and let us derive the expression for the rate constant and half-life. Considering this reaction, A gives rise to products. Now, as usual, it can be written as minus dA by dt is directly proportional to the concentration of A power 1. Rate of reaction with respect to A is minus dA by dt, right? That can be given as directly proportional to the first power of concentration of A. But remember, it is not this one what we have written. This power is determined only after conducting experiments, I told you. Now, this can be written as minus dA by dt is equal to, say, K1 into A, right? Now, minus, say, dA by A is equal to K1 into dt, right? Let us write this as dA by A is equal to minus K1 into dt, and we'll now go for integration of this. See, on integration, we get dA by A can be written as log A minus K1 into T plus constant. Okay. Now, this constant can be derived taking the time as equal to, see, at a time t is equal to 0, as discussed earlier, A is A naught, where A is, of course, the amount left. Left is nothing but what we have started with, because we are still at the point of starting or about to start next. Now, when t is equal to 0, A is equal to A naught. Similarly, when t is equal to 0, we can write, say, this becomes a 0, then the constant becomes equal to log A, right? Because this becomes a 0. Now, from these two, I mean, from this and this, it can be written as constant is equal to ln. A can be written as A naught. Substituting this in this expression, we get log A is equal to minus K1T plus ln A naught. Okay. Now this can be written as K1 is equal to 1 by T into log A naught by A, or finally this way. See, ln, I mean natural logarithm, is equal to 2.303 into log base 10. That's it. Okay. So this is a very important expression. Now, of course, the same can be written in some other format using that AX terms, 2.303 by T into log A by A minus X, isn't it? Because A naught is nothing but A initial. A is nothing but A minus X, left out. Okay. Now see, from this also we can derive another expression. Taking anti-logarithm, it can be written as, I mean, after modification, it can be written as A is equal to A naught into e power minus K1T. Now, if you take logarithm to this, you will get this. Okay. You know, this is called Wilhelmy equation. Wilhelmy equation. Even this also is very important. Okay. Just keep it aside. So this is how we can derive the rate constant expression for the first order reactions. And now the expression for half-life. See, at a time t is equal to t half, that is when half time is over, amount of the reactant A left will be A naught by 2, isn't it? Now substituting in the expression for K1, it can be written as a 2.303 by T is a T half log A naught as it is by A naught by 2, right? Then this can be written as 2.303 by T half into this, of course, is log 2. You know, this log 2 is a 0.3010. So from this, the final expression for a T half can be written as, you know, 2.303 into 0.301 is 0.693 by K1. See, there is no concentration term. I mean, no initial concentration term. If you observe the T half expression for zeroth order, it was T half was directly proportional to A naught. in this case, let me say that this T half is independent of initial concentration, right? Now, the same thing if you want in some other terms, see at a T is equal to T half, it can be given as reacted is equal to taken by 2. Substituting this in K1 expression, 2.303 by T half is equal to log A as it is, A minus X is A by 2. Now K1 is equal to 2.303 by T half into log. Of course, this is A by 2, nothing but log 2, nothing but 0.301. Come on, K1 is equal to, yeah, let me straight away write the expression for T half. T half is equal to 0.693 by K1. Okay. So, in case of first order, remember T half, I mean the half-life is independent of what the initial concentration of the reactant is. Okay. Let us take some examples. N2O5 gives rise to N2O4 plus half O2. This, of course, can be written as, I mean, N2O4 can even be written as 2NO2. Okay, no problem. But remember, even if you write the 2, 3, 10, whatever you write, this will, of course, be a first order reaction. Now, look at this. NO2 plus CO gives rise to NO plus CO2. See, in this case, the rate expression can be written as K into NO2 to the power 1, but CO to the power 0. That means order with respect to NO2 is 1, CO is 0. Means rate is independent of the concentration of CO. Okay, then whatever the stoichiometric coefficient may be, but this power is not going to change because these powers are obtained only after conducting experiments, right? Then the decomposition of dichlorine heptoxide into chlorine and oxygen. Even this also is a first order reaction. Decomposition of H2O2 into H2O and half O2. First order. Decomposition of ammonium nitrite into nitrogen and water is also a first order reaction, and more importantly, all radioactive disintegrations are of first order type. So these are all very important. In fact, all are interesting, important, but this is discussed in detail in nuclear chemistry, of course. Okay. Let us go for something very interesting. Pseudo first order reactions. This pseudo refers to something false. Okay. Pseudo first order reactions. They appear to be of second order, but are actually of first order type. So that is the beauty of this pseudo first order reactions. Reactions that appear to be of second order type, but are actually of first order, are pseudo first order reactions. Okay. Let me give you examples. The first one is inversion of sucrose. Now look at this reaction. Sucrose is hydrolyzed in the presence of acid catalyst. Sucrose is, of course, a dextrorotatory. It is hydrolyzed, taking large excess of water. Look at this, large excess thing. Upon hydrolysis, you get glucose, which is again of dextro type, and fructose, which is of levorotatory type. But levorotation of fructose is greater than that of the dextrorotation of glucose. So, if you observe the overall thing, see, you have started with a dextro one and finally ended up with something which is of levo type, levorotatory. So, this is what we call inversion of, sucrose. That is the reason why even sucrose is called invert sugar. Okay. See, in this, the point what I would like to say is whatever is taken in large excess is not going to affect the rate of reaction. So in this case, rate expression can simply be written as K into C12 H22 O11, nothing but sucrose to the power 1 into water to the power 0. So order with respect to sucrose is 1 and that with respect to water is 0. Overall, it is 1 plus 0, nothing but 1. You have taken two reactants, sucrose as well as water. But because water is taken in large excess, rate becomes independent of that. Okay. See, because it is taken in large excess, rate becomes independent. So this is the best example for pseudo first order reaction. Appear to be of second order type, but are actually of first order.